your task, the model works on this. And whenever you throw an image that has a bus or a tractor, it gives you a result. It says there is a bus or a tractor. Now, you see like this particular CNN model will extract features that will look for unique characteristics of this particular data. Right? Now, I'm going into another new task. Okay. I'm going into a new task. In this task, I have cars and motorcycles. Now, you see, right? So, in this case, if at all we want to train a model, we have to train the entire data set again with a very new model. Which means that new models will take more time again to be trained. We have to fine tune, we have to do a lot of steps. But if you see, like, there is one correlation between the previous data set and the current one. Previous data set is also automotive. The current data set is also somehow related to automotive, right? Which means that what if instead of me creating a new convolution neural network, what if I use the features from my previous model? What if I use a convolution layers alone to extract features for this data also? Will that work? So if you see, right, so in the previous example and the current one, so all are metallic structures, right? So all are metals, the paints, the background, the foreground, almost like all the scenarios will look the same. So there will be like, very less changes which you can see. But yes, obviously the shape and textures that will be different, but the environment and other stuff, since it's like closer to an automotive environment, it looks almost the same. So which means that when you extract some features, using the previous method, like which has been trained onto this model, can definitely extract better features for this data as well. Which means that you don't even want to train a model at all for this data set. So you can use the previous pre-trained weights, use that to extract features, and then train a simple neural network on top of it. So which means that it saves a lot of time, and you don't even want to train a new network on top of it. So this is how we call it as transfer learning. Okay. So what we do is, like, let's say a typical CNN will have input image, have some convolution layers, have a dense layer, and will give you some predictions. Now what I'm going to do is, I'm going to take the convolution layers alone. Okay, that is useful for my feature extraction. So I just stop it there. I extract the features alone. And those extracted features will be given to a newly created dense layer. So this newly created dense layer will have our own property, because the current data set discusses about motorcycles and car. The previous data set contains bus and tractor. So which means that I have to somehow fine tune the model for the new task. But the feature extraction can stay the same, because obviously both are all automotive in nature. I can use the same feature extractor. So that's what. So which means that I have to only train this layer. I have to only train this dense layer alone. That's more than enough for me to train a model. So imagine like how much amount of time you can save. It's humongous, right? So that's how a transfer learning works. So you take new sets of data that is going to enter into the convolution layer, which is being trained onto the previous task or some other bigger data set. So with that bigger data set, bigger data set, the model which you are going to use, the pre-trained feature extract network which you are going to use, will be much more sufficient to extract sufficient features for the new data. And once the features are extracted, the features will be given to the dense layer. The dense layer will keep it out. Only this area is your new classifier. Okay, this area alone you're gonna create something new, and you'll be done. Okay, so that's how it is. So what is transfer learning? So yes, you can also train new models for new tasks. That's also fine, but it's a waste of time and resource, because it's like almost very identical task. I don't want to invest a lot of time and a lot of training cycles to train one model for a new task, which is very similar to each other. So instead I can use a pre-trained model, extract features, get those features, just train your dense layer alone, be done with it. That way you can save a lot of time and a lot of resources. That's how at transferring. So it's like very similar like how you utilize your workspace. You have knowledge in mathematics. So when you start studying some engineering concepts, you won't be saying that I don't know maths because I'm studying engineering right now. It's not like that. You apply your previous knowledge to the current thing as well. Very similar to that. Transferring can. Now, how and where we can use this transfer learning? Why this concept has evolved in the period of time? Because see, not many engineers will be training very different models, right? So also the models which you train will be very different against each other. Imagine I train a classifier for bus and cars. Next time if they're asking me to classify a laptop versus phone, I cannot use that classifier. I cannot use that CNN because that's entirely different and this is entirely different. Because that's outdoor, this is indoor. So for those type of situation, this won't work. Imagine I'm doing some cancer classification, and suddenly they're asking me to do face recognition, face classification. These are two entirely different problems, which means that obviously I cannot use the pre-trained model for this because the feature extension will be very very different. So then how we can effectively utilize something which can be utilized for all the most of the problems which we have. So that's where transferring was not introduced, but a new challenge called this ImageNet was developed. Okay, so ImageNet is a challenge, where they have like close to 1.2 million training data. Okay, they have close to 1.2 million training data and 100k testing. So the test and the train set is almost very large. Okay, it's not just large; it has like 1,000 classes. Okay, not just one or two classes. It has 1,000 classes to start with. So if you see the classes, right, so you have all the common classes like a small insect like mites to a larger container ship, which is very large, and you have a motor scooter, you have a wild animal, domestic animal, some vegetables, some veggies, and automotive. So which means that like it is kind of a combination of all the elements together. So outdoor elements, indoor elements, wild animals, domestic animals, which means that this data set is a mixture of everything together. Correct? So if at all, we train a model on top of this, the model is going to be super difficult because it has many different varieties. Training such model is not that easy because your convolution network should be supportive enough for to do that. And it's not just one or two, it's 1,000 classes. Imagine the amount of effort which you have to put to classify 1,000 classes in a single shot. It's not that easy to do. So this has become a huge challenge in the industry, right? Even people are still using this this ImageNet challenge for classification approach. So whenever a new architecture comes into play, right? This ImageNet is kind of utilized. They use it as a benchmark data set. So if you are creating some new architecture, right? If you want to publish it as a paper, use this data set. See like what accuracy you get, and you can benchmark this in the common core. So that way your paper will get a lot of benefit because you are using a standard data set to benchmark yourself with your previous predecessors who have worked on different architectures to do that. Okay, so this, as I told you, this has become a challenge, and you see like many people have competed with it. Okay, so the beginning year it was like 2010, 2011, where the error rate is very very high. You see that the error rate is 26%, very very bigger. But the year goes on, right? So it goes from 26 to 16, 11, 7, and some point of time it became even more smaller than the human error rate. So the human error is 5%. Even we make mistakes on this 1 million images because obviously, right? We might not know. Like sometimes if you see this example, people might confuse between person and scooter. So they can even say this is a instead of a scooter they can say it's person. And sometimes yes, people might confuse with leopard, cheetah. So yes, some sort of confusion will also be there for a human being. So which means that the error rate of the human being is 5%. And can we create a model which can surpass this capability? Yes, at some point in time, the model which was developed was much more better than the human capabilities. Okay, let's see that. Yeah, so people, as we see here, right? So in 2012, this Alex Tech came into play. Okay, I'm not going to this network because this is the first ever, convolution network which was developed. So this was the first ever, convolution network which was created. It has like very less layers to start with. But let's not go into this network. Let's see this Alex network. Okay. So again, there is few key takeaways with this session. One is you can understand some different architectures, some standard architectures which you can replace for your model training. It's not like you can, yes, you can also customize your own architecture, but you can utilize the standard architecture to train a model. That's one thing. Because if you do some standard architecture, you can do a good benchmark. That's one. Second thing, you can use transfer learning approach, train models using transfer learning and see like how it works. You can use a domain adaptation technique, like training a model with a new domain of data. That can also be done. And overall, you get a skeletal code, a skeletal structural code, where you can utilize the code for any type of classification model. You can train it from the scratch, use a pre-trained weights, use transfer learning. You can use the same code for multiple approaches as well. Okay. So that's the agenda for this session. Okay. So if you see this AlexNet, right? As I told you, these are some standard architectures because they have been iterating with many times, to find the right architecture. And if you see, right, so they were the ones to use this ReLU activation function for the first time. Okay, you know about ReLU, right? ReLU activation function. This is the most important activation function for a CNN or for any neural network, for a free power network. Okay, so it was the first time that is ReLU. And they use heavy data augmentation, they use a drop of 50%, and they were able to train a better model out of this. So if you see, right, so you have the data goes into a convolution layer followed by max pooling, convolution followed by max pooling, followed by three convolutions followed by max pooling, right? So if you summarize it, it is convolution followed by max pooling, convolution followed by max pooling, and then followed by three convolutions. 1, 2, 3, followed by max pooling. So this is how it is structured. So you can also keep this structure for your other training. So for all you're going to create some customized model, for example. This can be of use. Okay, so let's say I want to train some new model. Okay, can I use a customized structure? Yes, you can use this as a guideline. So what they did, they use convolution, max pooling, convolution, and then after two layers, two sets of convolution, max pooling, they got with three convolution layers and one max pooling. That's one approach. Okay, and finally they have applied two dense layers that has like 2014 and 2042 neurons, followed by 1000 neuron output layer because you have a 1000 class category. So in order to digest all this information, they use two dense layers of 2044, 2048. That's like one layer of neural network, another layer of dense layer, then followed by 1000 class output. So this is how the structure is created, and they were able to get a result of how much? You see, like it's 16.4 as the error rate. So out of 100%, it's 16.4 as an error rate. Obviously, it's giving us close to 84% of accuracy for the given data. And if you see the data set size, it's like very big. It's not that just 1000 images or 1000 images. It's like billion images. 1.2 million images to start with. It's not that easy to train a model for 1.2 million images getting 85%. So which means the model is doing favorably a decent task on it. The performance is really decent enough to start with. But again, that was not the end. 2013, they created another network. This is called ZFNet. Okay, this ZFNet is an improved version of AlexNet. Okay, so they didn't do any change in the architecture, but they changed the pre-trained weights. The hyperparameters which you see, right? all those hyperparameters alone have been changed. So by just changing the hyperparameter way effectively, they were able to train better model with even more better accuracy with 11.7 as error rate, which means that with an improved version of AlexNet, people can able to create a model with a huge data set. They were able to get an accuracy of 89%, which is a very good model to start with. Which means that this AlexNet is much more capable enough just by tuning hyperparameters. What is hyperparameter tuning? You change the filter size, you change the number of filters, you change, you won't change the layer, but you change the filters and these values. Sometimes you change the activation function. So all these things can be changed to do a better model on top of this. Okay, that's one thing. And I would say in 2014, right, it got changed entirely. The way we look on CNN got changed entirely. The landscape of the CNN got changed because of this 2014, because of this one network called Google Net, or aka Inception network. Okay, which is one of the famous architecture. Still, people use the concepts, utilizing this network for many different purposes. Like how Google created a paper called Transformers that changed the entire history of LLMs. That changed the entire landscape of NLP looks like, right? So still they are using those components to work with. Very similar to that, Google had entered at 2014 this competition, and they have created a very useful approach, which changed the entire landscape of CNN. Let's see like what they've done. But before do that, we have another network called VGC network. Okay. So this is like survival of the fittest, I would say, because what they did, they tried with multiple combinations. They tried with n number of combinations to see like how many layers they can go with. So one thing about layers, more layers, what you will get? More features, that's one. But with more features, you get more complexity as well. The complexity of the data will be very, very huge. Because if you do the math, a simple math, right? For example, you have an undercross 100 image. First convolution, you get 10 filters, for example. Second, you have 10. Third, you have 10. Fourth, you have 10. Fifth, 10. If I keep on, increasing this, what happens? This is how many layers? 1, 2, 3, 4, 5, 6. Imagine I have like such kind of 16 layers with it. Which should be like 100 into 100 into some 16 times into 10. Imagine I'm using 10 features. And here how many features they are using? 64. Here 128, 256, 512. Which means like how many features should be there? Like very huge. And if you see this structure, right, it's one of the famous structure which people can use. The architecture layer seems to be like very intuitive, and it works for most of the problems. Okay. So what they have done, they have created 2 convolutions followed by max pool. 2 convolutions followed by max pool. After that, they go with 3 convolutions followed by max pool, 3 and 1 max pool, and 3 and 1 max pool. So which means they use 5 sets of max pooling, and they have used almost like two sets of convolution and then three sets. So one common thing which you notice between VGG and AlexNet, right? So initially they go with smaller number of convolutions for every max pool, but later stages they go with large number of convolution layers before they give a max pool. Correct? In this case also you do with 2 convolutions followed by max pooling, 2 convolutions followed by max pooling. After that you go with 3 convolutions followed by max pooling, which states that at some point the later information will become too focused, and once you start with more of such convolutions, your later information can be even more better. It can get even better at some point. But the biggest problem is like maintaining the identity of the data and also the complexity is, because the complexity will be like very, very high. Because if you simply calculate, right? So let's say you have 224 cross 224, right? So that was how many of pixels we have, cross 3. Oops, sorry, what happened? Shut up now. I thought like something was happening. So now we multiply this with 64 feature maps. And yeah, 3 is number of channels. From the 64 you multiply 128, and again I'm just talking about the channels only. Okay, so or what I can do is right. This is 3 channel. Okay, 3 channel into 64 into 128, and again this is not just 120, this is 128, this is again 264 into 64 into 128.
That's another one. There are three boxes.
Sorry?
There are like three. You have mentioned like 3 boxes. Two red, 2 blacks, and 2 white. So that is not necessary.
That is max pulling. Max pulling reduces the dimension. We don't require that. That's like just to reduce the complex. So you see, right? After these 4 layers, how many channels they have? Humongous, right? Simply I'm just 64 into 64 into 128 into 128. How much I get? 67,000 into 3 channels, which is going off the charts. Imagine like I'm going the same way till the end. How many feature maps will I have? It's too huge, right? It's like too much of complexity to handle. But somehow this setup was capable enough because of 2 reasons. One is they use sufficient max pooling to reduce the resolution of the image. Second thing is like it has a huge data. Since it has a huge data set, it can somehow compensate to this much amount of complexity. That's one thing. Another challenge with other areas is that you have how many max pooling? You have 1, 2, 3, 4, and 5. And you see the image size, right? What is the image size now? What if I use another max pooling here? You become 3 cross 3. Another max pooling will be ending up with 1 cross 1, right? Which means that to the maximum I can go with 7 max pooling no matter what. Okay, because like from it will usually divide the image by 2. For example, if you have 100%, first max pooling will give it 50, second will give it 25, third is 12, 6, 3 and 1. Right? So how many max pool? 1, 2, 3, 4, 5, 6, 7. So totally, no matter what image size you use, you can go to a maximum of 7 max pool. Even 7 max pool is very high because you will be ending up with having just 1 cross 1 as an output. So imagine from an image size that big, you just get 1 cross 1. What information you will have? You will have nothing in it, right? So that's also very important. So you should not be overboarded by adding more convolution layers. That might increase the complexity. And you should not overboard by including more max pooling layers. That will reduce the dimension. And one more key factor behind this, how does a convolution works in the first place? For example, let's take an image. Let's say this is my input image that has a phase in it, okay? Something like this. Now, first feature extraction, first layer of convolution. One convolution feature will focus on the eye region, okay? One will focus on the mouth region. One might have focusing on the entire skeletal section. This is first feature. Second feature layer. Now this eye region will go a little bit close by. It will look for the iris region. Just the iris region will be like located. Here it will look for the maybe like jawline or the lip region. This will go for the jawline or the head region. Third convolution. Inside iris it will look for some more patterns. So at some point in what happens, right? It extracts feature onto feature onto feature. It becomes more diluted. It becomes more constant to a certain point. At some point, after 10 or 15 convolutions, right, you will have random dots here and there. You won't have features at all because you won't even have any data to start with because you have extracted a lot. See, like how much you can zoom. You can zoom onto a person, and then you can zoom onto the face. You can zoom onto the eye region. You can zoom onto the iris region, pupil region. With microscope with level. At some point, you'll be done. With 10 iteration, 20 iteration, you'll be done. That's for sure. That's what happens. So you cannot go with more convolution because it will destroy the identity of the image. At some point, it will become garbage noise, and this will decide your output basically, right? Because the last convolution is directly to the dense layer. So whatever garbage information you get here will be given to the dense layer, and that will not help the model to learn because this is like totally unlittered term. So you have to make sure you strike the balance of having these twin layers, because beyond that it won't give you this. That's one thing, and you unnecessarily increase the complexity. That's second thing, and you cannot go with more maximum. So with these three, conflict of interest, these three combinations, BGG network was trying to do justification like how much they can do. And this much they were able to do, and they were able to get better results. And one important thing is that since they use 5-6 max poolings, they were able to have a very lesser parameter than Alex. Because if you see Alex argument is very simple, right? Even though it is simple, you have more dimensions. Even though this is big, you have lesser dimensions because of the max pooling, which is because there you just use 2 max pooling, you are using 5. So it is the dimension of the image is greatly reduced, which means it has a very slighter parameter than the Alex thing. That's one thing. Okay. And what is one more thing? All the 16 layers contains 3 cross 3 as a filter size. All the filters which has been utilized will be utilizing 3 cross 3 as the image filter size. With this, they were able to get pretty decent result. If you see, right? So they were getting like 93% as accuracy. 7% was error rate, 93% as the accuracy in 2001. But in the same year, Google Net was also introduced. Okay, BGG is from Caltech, I believe, Caltech or some good university they have created this. But Google Net, obviously it's from Google. They also called as Inception Network. So they created a very different concept here. Okay, few key takeaways are like they use 22 layers, which is even more bigger than the BGG network. That's one, and they use no fully connected layers at all. All the classic CNN should have a fully connected layer because that's how they digest all the information together. So that's how the nature of CNN works. But this method, they tried avoiding the fully connected layer. They rely just on the convolution layers alone. And it has been proven that it has 12x lesser parameter than AlexNet. It's another surprise because it's a very big architecture. And still they were able to compete with the very less parameter especially because of this fully connected layer. Because for every architecture, fully connected layer will always increase the number of bits. Okay, if you see our example, right, in our auto code also. So where it is spiking, so you see, right, from this flattened variable, you go to a dense layer of 8 neurons. How many weights you get? You get 25,000. So basically, whenever you have this dense layers, your weights will explode. So they didn't make sure, okay, so they don't want to have fully connected because the weights will explode a lot. You will have a lot of weights to consider. They removed it. Okay, that's one thing. And one more thing is like, you see it, so they have a different concept, like, they use a layer, from that they expand it to multiple set of combinations. Like one will be going with 1 cross 1, 3 cross 3, 5 cross 5, something like that. So which means like you do multi-convolutions, different size filters for the same feature maps, which none of the architecture did. Because every architecture just push it either 5 cross 5 or 3 cross 3 or 7 cross 5. But this guy created a method that uses different size convolutions for the same feature. But again, if I use multiple convolutions for the same feature map, that will increase the complexity because I'll get a lot of feature maps for sure. But how did they maintain this problem? Even though, despite the fact they have 22 layers, and it's not just 22 layers technically, they have a lot of convolutions behind it. Which means that every convolution will get a lot of features. It's like typically, I would say these are like 3 layers. It's not just 1 layer, it's just 3 layers. But they claim this as one single layer. Okay. So, what improvement they have done is, the most important part is this 1 cross 1. This changed the entire landscape of Google. Okay, so what did it do? So they used a concept called 1 cross 1 convolution. Okay, that will make sure what feature maps to be extracted. Let's say if I use 1 cross 1 cross 32. And this is my intermediate output, like say 20 cross 20 is my image size, and my feature maps are 192 are there. At this current layer, I have 192 feature maps. So now when I use 1 cross 1 convolution filter with 32 feature maps, Now this guy can only accommodate 32 feature maps. So out of this 192, you select the most important 32 feature maps alone. This means your feature maps will not explode. You can maintain the feature map because you can obviously see you have 2 lakh feature maps. Obviously, all the 2 lakh feature maps will not be important. Only like 1,000, 20,000 feature maps will be very important. So it's unnecessary you're traveling all those feature maps to the next layers and increasing a lot of complexity. So with this one crossword convolution, you can reduce that by maintaining the diamond stacking. Okay. So the number of features, if you feel like you want to only have 32 features, you can just use one crossword convolution followed by 32 folders. Which means this one crossword convolution will just hold 32 feature maps. That's all. So this one particular concept, right? This one crossword changed the entire landscape of CNN because now this has paved a way for people to go with a very larger convolution layers. They can even go 50 layers, even 100 layers. But the only problem is like now the biggest problem is solved. You don't have a complexity because you maintain the feature map size. But still, the understandability of the data will not be there because you have no features at some point because you lose the identity of it. Right? So now this was successful, they were able to get good results, they were able to get 6.7 error rate, which means like close to 94%, which is very on par to VGG. But in 2015, that even got changed. This was the first year a network beats a human being, in terms of computations. They were able to get, results in a much more better way. So if you see here, right, this particular network called ResNet has how many layers? 152 layers. Imagine I was saying like just going with 10, 15 layers, you can't maintain maintain the problem of all the feature maps will not be really good. Then how can I go with 152 layers? Is that even possible to do that? Will my features hold up? Very tough, right? Let's see like what they have done, and this is particularly done by Intel. Intel's team has entered into this competition. It's a healthy competition. Even now people are doing that, right? So Intel, Facebook, Google, all compete with against each other. They create their own models and their own ways. It's very similar to what we see here right now. In the previous days, also it was the same. Once Google entered, ResNet, your Intel competitor of Google entered. And they were able to succeed even more better than the Google guys because they used a concept called identity mapping. What? Identity mapping. So what they did, so as I was saying at this example, so whenever you have a feature, this is a face, the first feature extraction will only have the eye region, one feature will have the lip region, right? But if I go focus on this area, what happens? Eye region will be focused onto iris and something like that. But what if I take this eye region and I add it against to the original image? Features which I extracted, what if the extracted features are added to the actual image itself? I take this and I add it back, which means that next time the image looks something like this. This region alone will be like little highlighted because that's how the feature is extracted. Next, the features are lip region. So this alone will be like this. Yeah, you do identity mapping, you overlay the feature maps onto the original image so that the original data will not be lost. Yeah, it's not like, it's just an example which I'm trying. Usually like what we do, right, so we see the architecture, like you start from here, right, you do some convolutions first. Those feature maps will be there. Initial feature maps will be rich in information about the identity of the data. With that, you superimpose, you add the values together. Like whatever feature extraction you've done, you add that feature values with the actual input value. So what about when these two guys are added each other, the identity can be preserved. Because you always refer to the actual image. You add on top of the image. Which means the identity will always stay the same. You will not lose that. Because at some point you lose those feature maps because it's been lost. You are just focusing on some important sections around. Yeah, it will never lose identity at all. Even though you go these 12 layers, you can extract good information, but the identity will be preserved. Since the identity is preserved, even though no matter how deep you go, you won't get lost. Because you have the identity, mapped on top of it again. So that's how they have tackled this problem of depth. Because now people can easily use 1 cross 1. Here also you see it, they use 1 cross 1, they reduce the dimension, they use some convolution, they again use 1 cross 1, get it as 2 to 6, because your input is also 2 to 6. 256 plus 2 to 6 will give you same 2 to 6. But you add this input data with this output data. You see it? This is being added with it. This is called skip connection. You use a skip connection to do this thing. Got it? Got the idea? So it's a 152 layer model. It's not just 1 or 2 layer. It's like 152 layer model, and it's not fully connected against each other. Okay. So that's how different model was evolved. Okay. So you have we did saw the evolution, right? So we get started from the shallow networks and we started with AlexNet, VGG came into play, we have GoogleNet, we have ResNet. Now we also have VID transformers, vision transformers. There are many architectures that have been developed and things are becoming better and better. But now people are focusing toward lightweight models so that they can deploy it in their mobile phones or something. Because nowadays people are looking for a better model for to be running your edge devices rather than running in a server or bigger systems. Edge device is the way to go. So on that account, this proves to be the some evolution which you can keep. So what are the key takeaways which you can keep in your mind? One is these are some standard architectures. You can utilize these standard architecture and train something on top of it. That's one. Second thing, you can use a transfer learning because these architectures, as you see, these are like very big architectures. I can use this as a feature extractor because these architectures have been trained onto a very large data set. The data set which you see is like going to be like very large, which means that it knows like how to extract features for any data which you give because it has been trained onto very commonly available data, right? So if you see this example again, you have bigger shapes, small insights, indoor, outdoor, all these things are mixed properly. Next time you use the pre-trained weights to extract this feature, you will extract for sure. You can extract this water bottle feature correctly because it knows on a given image which should be important, which should be not. Because 1.2 million images with a bigger architecture, the model gains superiority and understanding like which features to be extracted and which features to be not. If you have a photographer, you're asking him to, he's a wedding photographer, and you're asking him to do some events. He knows the drill, you have to look for the important modes and things. Very similar to that, this particular pre-trained network is sufficient enough to extract relevant information for any data set which means that, yes, because of this challenge, imagine your transfer learning came into reality. So it was a concept long buried, but because of this ImageNet and people saw the potential of these networks being trained onto a very large data set, people utilized transfer learning to make things better. Okay, so this is how our transfer learning works. And there's one more concept called domain adaptation. I'll come to that point a little later, but you got the idea, right? So do we have any doubts or clarifications? And you see the results, right? So these results have been tested on this 100K test data. Okay, so since the result became promising enough at some point of time, what they have did is like Google created another network where they utilize ResNet and GoogleNet together. Instead of having just ResNet, they use the ResNet architecture, but they also use the GoogleNet's multi-step approach. So with these two combinations, right? So they were able to create a concept called GoogleNet V4, which was even better than the ResNet architecture. If I take this data set, right? So this is benchmark results. Now we can see like where they are in right now. You see, right? So this is the evolution. Since it was AlexNet, VGG was there, Inception V3, ResNet, some simple net, and then you see that these are other networks which has been developed. We have EfficientNet, which is one of the famous architecture. We have Coca. Like this is the top model within the industry. using 900. So you'll be seeing this number and that will be a little different because that uses a no, that's the old data set. But this is a new refined one where you can see even your RESTnet is having just 81%, it's having a rate of 19%. But the result which you see is a little different from what you see here. But this is the, the final value which you get. Okay, so out of all models, you can, model not using external trained data, model using this one. So I would say by far this was a model, which called bedrock. So you can always use this paper code, website to see what are the papers have been done. We also have image at 1K data set, just 1K images, just to quickly benchmark. This is also, you can just see whether there are some papers involving transformers, whether this paper involving RESTnet and transformer, or just the RESTnet alone. Because you can search it, you can see that the top accuracy which they have right now is this network, big transfer, BIT, general visual inspection, representation learning. You also have the GitHub repo. Search for it. See what they have done. Likewise you can always refer to the benchmarks and the code base as well, and see which one you can complete. Okay, likewise you can always look for the benchmarks, state-of-the-art networks can be always seen here. These are SODA, segmentation, optimization, image classification, representation, contrastive learning. All the SODAs are for natural language processing. You have language modeling, question answering, medical, miscellaneous, methodology, time series, graphs for every problem, right? Even till music generation, pair swapping. Everything is kind of collected here. Papers and Code is a very good place to look for benchmarks, which is the latest model and what they have done. If you want to compete with them, you can always utilize these website, papers with code /SOTA. SOT, state of the art methods. Okay, so yes, obviously it shows you all the data set methods and everything. And the most important part is they almost give the information where they kind of have the codes for it. Okay, usually they will have papers with that as a code base in it. Okay, so you see that the latest optimization code data, right? So that's the latest model, and you know that we got even YOLO V12, which is not updated here. But yeah, that's what. So likewise, you can just browse the state of the art to get some information. Alright. So now we'll go to the programming part. Let's see how it works. Okay.
Tap and pay Google Pay இருக்குல்ல அட நீ வந்து உன் கார்டு வந்து Google Pay ஆக்செப்ட் பண்ணிட்டேன்னா NFC மூலமா போட்டு அப்படியே ப்ளஸ் வந்து டேப் பண்ணனா பேமெண்ட் அமௌண்ட் தெரிஞ்சு அதெல்லாம் ஆஃபர் நான் வந்து Google Pay கேளு Google Pay வந்து ஃபர்ஸ்ட் டைம் பே பண்ணனும் மேலே பண்ணா நான் வந்து போட்டு டேப் பே பண்ணேன் பெட்ரோல் பங்க்ல ஸ்டோர்ல போய் நான் கார்டு மஷின் ஸ்கிராட்ச் ஆகி அதெல்லாம் கேட்டு
Okay, so just we have two programs here. One is this same repo, same model. Just set this pre-trained model first. So first we'll utilize this pre-trained model to classify images on the fly without even training it. We'll see like how this pre-trained model works in classifying stars. Okay. So yeah, so I'm just loading this repository because I just loading some images here. Okay. Yeah, just to load some images which I have in my GitHub repository. I'm just loading this repo. But before you do that, just make sure you have the runtime text for GPU. Save it. Then clone the repository first. This is just to make sure I download some images to my collab space so that I can just infer it and see it. So just doing it. And you say I'm importing these 16, 19 and REST 50 and inception weights. I'm just importing these four models. Okay, I'm going to load the pre-trained weights and I'm going to see like how it works on a generic image. I'm not going to do any pre-training or transforming. I'm just using it just like it over the shelf. See like how these network works in the first place, because that's like how they claiming it to be very effective, na? So I just load these packages or the libraries. Now you see right, so I have loaded four models, like model inception, model Preston and model VGC98. So there are four models I'm loading right now to see like which gives different results. And yes, you can get a summary of all the models. VGG19 has how many parameters? 14 crore, which is 1.4 billion. No, sorry, mistake. 14 million. It's like 14 million parameters for VGG19. If I see the summary for VGG16, it is 13 million. 13 million. Let's see about ResNet and insertion V3. Okay. See the parameters for inception. Right. So if you see for the parameter inception, it is 23 lakhs only, right? Which is way less than the normal, because of the no fully connected way. It gives you better, smaller details because there is no dense layer at all. Okay, and if you take the inception model, inception. Restaurant is also having very similar values. Okay, so yes, which means that like ResNet, GoogleNet is having 25 lakhs, but when you take VGG and VGG90, it's like a little bigger than that. Okay, because of the fully connected layer, when you have a lot of layers going around with lesser, control in the dimensional space. Why VGG and inception is much lesser in weights? Because it doesn't have dense layers and it can also control the number of dimensions it's entering using the 1x1 filters. Okay. But anyways, I'm going to use this model. I'm going to load an image. Okay. I'm going to load an image, convert it into a format where my Keras can able to understand. Okay. Load an image for inception as well. Get it to VGG. Predict the class for VGG. And you can transfer inception and testnet. I'll just put everything together. Now you can see prediction, coming for different methods. This is for VGC60. This is what we're getting. So the image which I got is an African elephant, which is correct. Okay, so you have an African elephant here. So what about the next one? What about inception? Let's see the results for inception. So the accuracy of inception is little higher than the EEG, right? Because you see, right, the confidence is in detecting the African elephant is 95. Here it is 68. And what about EEG 19? 74% of confidence. What about ResNet? It is 80. So in this case, yes, obviously ResNet is the best model. But for this case, ResNet is having lesser confidence than the inception. But that's fine. Obviously, it is somehow all the four models have pointed towards the same, output, which is one good thing to be noted on. But there is a dilemma. If you see the actual, actual image, you will know. So you have an image of elephant. So this is an African elephant. Right, so the looks of it, we can always say. So the model, all these four models are built into this as a class. So this is how the pre-trained model is. This is how the pre-trained model works with the first model. Now, yes, obviously, yes, sometimes, right, if you want to use some classification, like laptop classification, to classify human beings, classifying animals, something like that, then you don't even want to train a model because you already have this kind of model. You can use a pre-trained model and do it. Very similar how you have it for object detection. Everything has a pre-trained model with it. You will very well use those pre-trained model to get the results directly done without even training such models or not. But that's not the end. But we'll also see like how to train our own models and get some results done for us. You can upload any image. Program it right. Go to the next one. Just give it 5 minutes to try this program. Just try uploading some different images, see like how it works. Try with those core models and see like which model gives you good content. Try these things. In 5 minutes, you just give this program a try. Upload any image, see like whether it gives you a result.
OpenAI company
You can even upload your image. You can even upload an image here. OpenAI, for example, say like
Microsoft invest பண்ணிருக்கு
upload some image here.
அது வந்து OpenAI invest பண்ணிருக்குன்னு சொல்றேன் Microsoft
Let's take this one. Okay, so just upload it here.
வேற பாட்டி கொடுத்துருக்கோம் போடுறது வணக்கம் இருக்கு.
Copy the path. Okay, now I'm just going to give this path to all this
ஆமாம் ராம்
four pillars. This is how you change. Change the path for this one. Change the path for this one as well. Now let's see how it works. Shows what? On the model shows it is golden retriever, correct? Golden retriever, correct? And yes, exception is also saying this golden retriever. Every model is saying as well. So which means that yes, I can upload any model, any image. The model can give you good results on the model. Okay. But this is just again pre-trained model, and we have a long way of creating our own custom model. Okay. Just give this a try, and we can start in a minute.
நாற்பத்தஞ்சுக்கு 3 மணி 2
Pre-trained and transferred.
ஆனால் நேற்று வந்து
Pre-trained is the one using it.
See, that's very I thought it was very confused. Somehow it is getting Chihuahua.
ఆ లెవెలే వేరు అవును
கோபி சொல்லுங்க நாங்கள் 2 பேர் இருந்தாலும் அவ்வளோ தூக்க மாட்டோம்.
And for the next program, right? So it might not be, it will be a little difficult to run this program from your side because the data set is a little bigger. So I couldn't able to load in the GitHub. So I have it in my Google Drive. Okay, you can just download the data set and upload it into the Google Drive. Okay. So if you upload it in Google Drive, yes, you can use this program to run. Okay, so the program name is transfer learning. So just zoom it a bit. So you have Deepan Rajyam, you have the repository, and you have transfer learning as a program. Okay, so use this program. This is for your classification approach using transfer learning and using few different approaches which you can run the same program. Okay. So in order to do this, in order to run this program, I will be sharing you a link. From there, you can download the dataset and you can write it. Okay. But you have to upload it in the Google Drive, something like this. So you have to download this particular data set called cars. Okay. This data set is available in my link. You can just download this cars data set and paste it in your Google Drive. So how to do that? Just go to this link. Okay. Link3.e/deeper Just go to this website. If you go to this website, you can get to the data set. Okay, and also the presentation which are for this sessions. Okay, so if you go to this website, you see it. So you have classification data set here, na? So this tab, you can just click it directly in Google Drive path, and you can download this data set. So download this data set, and then you can upload it to your Google Drive. Okay. So go to this website, link3.e/deeper. Okay, and click onto classification dataset button. You will be entering into the Google Drive. From the Google Drive, you can take the dataset and copy and paste it in the Google Drive of yours, so that you can start it. Okay, just give few seconds of time to get things done. Go to classification dataset. Once you click this, you will be going into this classification dataset. You will get this Google Drive. This Google Drive have this dataset. Okay, just copy this dataset, download this, and upload it in your Google Drive so that you can use this dataset for model train. Okay, because this is little bigger, I can't push it in my GitHub. Or else, if you have your own dataset in a format like this, let's say all you have to do is create few folders that has some folder names. This folder name will be considered as a label. And inside the label, inside the folder, you can have all the data. Okay, this can be, this program can be applied for any classification problem, provided you maintain the structure. You have all you have to do is just maintain. If you have 3 classes, maintain 3 folders. Folder name should not have any spaces. It should be like solid. But those names will be considered as the labels. And you can add as many images as you want inside this folder. So all these images will be considered part of the trains. So that's how this program is created. It's like created dynamically in a way it works without any problems. Okay, so just download this from this website. Download and upload it to Google Drive. Right. Alright, so let's say once you've downloaded and uploaded, right? So you can just listen and you can try this out after some times. Okay, so let's go to the program right away. So first things first, I want to load my Google Drive, and it's always a convenient way using Google Colab and your Google Drive because you can load all your data set inside there and you can train a model on top of it. Okay, so just run this first line, you connect to your Google Drive. So make sure this Google Drive has your data set in it. So on the Google Drive, continue. Yes. So once it is loaded, you can see the entire Google Drive is loaded here. So inside this, my drive, I have the cars data set. So this data set has all the images which is prepared. So I'm just using these 2 folders, but you see that this is a very different data set. I just created out in the blue. you see them, I just take images of Ferrari car at different viewpoint, different angle and conditions. Even this image is considered, even though the cars in the background, I'm just considering this as well. Okay, very similarly, I have Honda cars. It looks something like this. So it's not just logo, sometimes even logo will not be visible at all, but using side angle or something like that, people associate with this Honda Ferrari. That's the idea. Now that I mounted, I import some packages here. Okay. So this packages includes image data generator. That is basically you can even create models with augmentation. Because even let's say you have some data set, you want to do some augmentations. What you will do, you do augmentation, you save it in a Google Drive or save it in a space and then use those images. But what if you do it on the fly? You have some augmentations. The first epoch you augment it differently. Second epoch you augment it entirely differently. Which means that at every epoch you get an entirely new augmented image, which will be even more better in terms of generality. Rather than saving some augmented images like clippings, cropping and all these things and saving it as an image, you don't even want to save it as an image and spoil a lot of memory. In this case, you just have to use augmentation on the fly. Okay, that's how many standard architectures. So which means that we'll be using augmentation on the fly. Every time the image goes inside this augmentator, it augments the image and it pushes to the model. Next time the same image goes to the augmentator, it augments it a little differently and pushes it to the model. Which means that like every time the model gets a different output. Okay. So that's it there, and we have VGG16 network which you are going to load in here. The many things are like pretty much the same. So all are like basic entities which you see. Okay, let's like import all these packages. And yeah, this is where your data set is loaded. Okay, so what I do is like I use a strain data set. I create some augmentation parameters, descaling, shearing, zoom, horizontal flip. What is shearing? You just twist the paper like this. This is called shearing. Not tearing, it's shearing. You shear it. You rotate this page. For example, this is the tissue. You rotate like this. This is called shearing. Sometimes you can rotate like this, like this. So all those geometrical transformations, right? So all these things will be done inside the shear. Okay. Affine transform, basically. You do an affine transform, so that you get a lot of varieties in the image. Okay. You have interzooms, you have horizontal, all these things. Okay. From this data set, you take 20% for the testing. Okay. So now the training data is given to this part. Testing is also given to this part, but only takes up 20% of the testing data. The remaining percent of the data will be used for training. Okay. So with this approach, you can load any data set and the labels will be loaded automatically provided this structure. Dataset slash and folder names. These folder names will be considered as the labels for the data. Okay, let's do that. Okay, how many images have been found? We have close to 518 images that belongs to the training data and 129 images that belongs to the test data. So overall, we have like close to 125, 627, somewhere around 630 to 650 images. Okay, that's why I couldn't able to load check data because they like size up little bit. Now this comes the important part. Okay, so you can use this problem in 3 different ways. Okay, I'll do the methods here. First approach, you can use it as transfer learning. You can utilize transfer learning. Classic transfer learning can be done. And let's say benchmark models trained from scratch. Benchmark model trained with weights. These are the 3 strategies which you can apply. There is also a 4th strategy which I will tell you, I'll just give you some pointers over there. So you can use a very regular transfer learning. You can use a base model trained with the scratch. A base model trained with the pre-trained weights. So these 3 techniques can be applied, and yes, this is more than enough to create different varieties of the same method, see like which one works better. Okay. So first what I do, I just call the base model. And the base model contains VGG16 that loads the image net weights, because this image net weights are kept loaded up to extract all the important features. So I give the input shape and everything. So this base model is loaded with the VGG16 pre-trained weights together. Okay. The output of the base model is given to the head model. And the head model contains some pooling strategies and flattening it out, some dense layer, and then finally one denser that will classify with as SR. And then you combine this inputs, like model input should go inside this VGG network to extract features, base model input. Output will take it from the head model. Okay, this is done. And this is where it comes important. Okay, so for layer and base model dot layers, layer dot trainable is equal to false. Okay, if I give it as false, what happens? The model training will happen only for the dense layers, only for the head model, like this model alone. This model weights alone will be loaded and be trained, will be fine tuned. But this model, the base model, will not be fine tuned at all because I'm keeping it as false. So this is how a transparent works. Okay, transparent because in transparent the base model feature extraction will stay the same. You won't even update the weights. Only this layer will update. That's what I'm doing. If at all you want to train it entirely, you just make it as true so that the base model will also be updated with the pre-trained weights. That's strategy number 3. If I give this as none, this will be training from scratch. So you can either train an entire VGG model from scratch, or using pre-trained weights, or using transfer. So these 3 approaches can be utilized in this one single program. All you have to do is change this program, change these components, you get it done. Okay. Yes. So you have this, your learning rate, epochs, backspaces have been given, and yes, you compile the model. And you can store the best weights. For example, sometimes you train for 100 epochs, right? Sometimes you get a weight at 80th epoch, which is the best one. But it might override. But making sure you get the best weights, and you always look for the I'll monitor the validation loss. Whenever the validation loss goes as minimal as possible in the previous checkpoint, I will save that model. Because I'm just going to save that model, and then I'm going to show you the the actual outline, like how the model has been trained for every epoch, what's the accuracy, what's the loss for it. Okay. And then I plot these curves. And once I'm done with that, I'm just loading some images to show you that how it works. Okay, let me just run this. But again, it will take a lot of time to train on. Let's see whether it works seamlessly without any issues. So this is the architecture we are using. If I'm about to train this model entirely, I have to train with this 19 lakh weights. But luckily, we're not going to do that. We're going to start it from here. We might be having 47 lakh weights only. Why so? Because even though we have dense layers, this has too many numbers, right? There's too many numbers enters here. It actually becomes very big. Even though I do transfer learning, I end up with 47 lakh weights. But if at all, sorry, 47. Yeah, it's like 1 million weights here, like 1.94 million weights. Right, so 1 crore or 1 million you could name it, okay, whatever your naming and that, yes. Okay. Anyways, so the weights will become three times the higher values if you're using the entire model for training. But since I'm going to use only this area, only 47 lakh weights going to be updated. Okay. Now we see that the model has started training, but the training will take a long time because of the model size and the weights being. And the data set size is very small, but you can train. This is how you can do it. Okay, so you can train the model, you can save the best weights, look for the loss curves. Loss curves indicates like how the model is performed, like overfitted or underfitted. If it is overfitted, you will get a very less training loss, but a huge validation loss. The accuracy of the training set will become very high, but the accuracy of the test set will become low. This is called overfitted. Opposite towards it is underfitted. So these two are very important to look for. So these two occurs in your model, don't use those. Just make sure it's like good or save the model before it overfits. With those informations in hand, you get a better model out of it, and you can even test with some images like this. Okay. So this will take some considerable amount of time because we are training everything together. But as I told you, yes, here I made it as false. What if I made it as true? This will take even more larger time to train on because it has a very huge data set to start with. Okay, so with this you can do a transfer learning, you can do a model training from scratch, and either from scratch or pre-trained model. So three approaches can be done with this one single program. Okay, give this a try. So you can fuse models. Okay, so you see, right? So I'm fusing two models together. Like one is base model and one is head model. I combine these two things to create one single model on top. Okay, so that's how things work. Okay, just give this a try. Train this model. You try all these three varieties. See like which gives you best results. But it might take some time to train on. Okay, so maybe after some time you can just use it. But just load the dataset, upload it to your Google Drive, map it correctly, and then to run it.
Otra vez